Hi, I wanted to talk about my summer project. So I have been working on this PMOD that goes for a FPGA development board. Um, there are a lot of 16-pin connections on FPGA boards, like this one, where you can connect a lot of different breakout boards with different components on them. And so this one has a 96 by 64 RGB OLED display with a 16-bit or 8-bit color resolution. So with this, you have an array of 96 by 64 pixels each pixel is dictated by either 16-bit or 8-bit RGB values. And so I wanted this because I wanted to dive into a little more complexity with learning more about serial communication protocol with SPI by being the master driver of the SPI module, unlike serial design, where I'm on the receiving end of it. And I also wanted a way to better display information for my state machines and whatever I create in the future. So my goal with this project was to create a SPI module that could interface with this OLED display and turn it on and reset it. And then also, if I could provide it ASCII values of a certain resolution for a width and a height, that it could display them based on an array of bits that I provide. And my thought with using the ASCII values was I could store the 1 byte ASCII values for each tile that's 8 by 8 bits, instead of storing 96 times 64 times 8 bits for each pixel and the color respectively, to try and save space in the FPGA. But I'll kind of step through how I designed the SPI module and then my progress on the OLED interface. And so before that, I'd kind of like to show how the project went, just to get an idea of it. So this is where I started after I first got the SPI module working and I was able to send command bytes to the OLED controller. So you can see that it turned on and started displaying something, but it just shows you this TV static gunk. Then I was able to clear the screen and write everything with black, and then draw a 1 8 by 8 bit tile in red here of a solid color. And so by this point, I wasn't converting any ASCII values, but I was setting the start and end row and column addresses so it would only display in this 8 by 8 bit zone. Because otherwise, if you set the start and the row ends to go all the way across and all the way down, it's just going to keep writing in a horizontal row, or keep writing each column, and then go to the next row, and the next row, and the next row. Then I was able to have a constant ASCII value input to the OLED interface module and display them. And it kind of looks like the FPGA is screaming for help, which it might be after it has to deal with me. But the screen tearing in here is just because I took a picture as the screen was refreshing. It doesn't do that when you're actually looking at it. And then I got some text to display. Again, this is hard-coded outside of the module. I just had it wired to the synth module that I made to synthesize it top level. But you can see here, but the letters are actually flipped. And this is because the ASCII to 8 by 8 bitmap was actually inverted from how I read it. And so what I did was I just flipped every row of the 8 by 8 bit ASCII table backwards. So each row of 8 bits was just inverted. And then you can see that that worked where I can have actual words, but it's actually offset here. And so this issue was found because I counted the wrong number of ASCII values to display. And so it defaulted to assigning them from the lowest bit up. And so it didn't have room to fill the top 4 bits, the top 4 bytes of ASCII values. And so that is what was first read for the display, but since it was empty, it didn't display anything. And then everything else got pushed to the side. But then we got rid of the dots because that was used for helping me debug, and I got all my text centered, and I was able to hardwire specific ASCII values. In my other FPGA video I did around Christmas time, I made a little timer game. And so before, this was on the 7-segment display. But so the idea is when you hit start, you will have to wait until... It's happening pretty fast. So you have to wait until the screen goes blue, and then you have to hit another button before it hits a second. And if you do, the timer stops, and then you get a good job screen. And so it was really nice because I was able to use the color to show the reaction better. I was able to explain it with the text on the game, get that real-time data coming back like you would on a 7-segment display with the timer, but you get a lot more information, being able to describe it, being able to update the background color. And the nice thing about this is I was able to pair a module I used previously and just route up a couple more state signals. And then I had the OLED display that I showed previously. I had the timer module, and I had a timer ASCII interface module where it pretty much, based on the state of the state machine for the timer, I would display these 4 screens and handle the output of the last screen with a case statement based on if you hit the button too early or too late, then you would get a too slow or too fast with a red background. But if you succeeded, you would show the time and then say, it's green, you're good to go. And so I'm already thinking of so many different opportunities to use this, and I think this is a very aggressive project to do. It was very challenging for me, and I learned a lot from it, especially being a self-guided project for myself outside of school. There is a class that handles like graphics drivers in school that I'm probably going to take next spring, but this was on my own for now. And the amount of information that I've got from this is amazing, because now looking back at when I synthesized a MIPS processor on an FPGA in school, I could use this OLED ASCII display to show what the current instruction was being decoded, or what was going through the ALU, or what kind of operation it is, or what's being fetched from memory, or what's going on. Is there any error flags from overflow being indicated? And what's awesome is I can just pair this with that code and then just write an ASCII interface to display it, and then this can also happen separately, concurrently. And I can just have it hooked up to this little PMOD connector right here, and it can just be off doing its own thing, just feeding me more information. So the goal is to use both old and new modules I designed to get more information and further understanding and clarity, because this is a lot clearer than a 7-segment display and 16 LEDs. And the way that I've designed this module is it's going to be just as easy to implement by getting the current state and whatever values you need from your state machine. Because as long as you have the data coming out of the module, which you probably already do because it would have been going to a state machine, and you just output the state alongside of it, you can determine, okay, what state am I in? What do I need to be displaying or describing? And then you just go through it, and you just have a lot more options to choose, because now instead of 4 7-segment displays that would give you pretty much 4 ASCII values, you have 12 columns times 8 rows. And then you can put in either hardwired text, or you can have, like we saw here, values that act as a counter or some other modifiable thing. And so I don't have to touch that when it's running. I just feed it the values in out from the other modules, and it's good to go. So I'd kind of like to talk about how I made this and what I learned from it now that we see the usefulness of it, and kind of why I wanted a little more complexity this summer. So to kind of overview what we need here, I'll talk about the pinout to the PMOD itself. So the way that the PMOD works is there is an OLED driver to handle the OLED screen. And so there's a couple different modes that you can use it in. It's already hardwired with this schematic for the PMOD to be in a read-only SPI mode. So the FPGA acts as the master, which drives the chip select pin, the master out slave in pin, and the serial clock. And then it also controls the data command control, which is used for the OLED controller, and then a power reset, and then some enable pins to turn on the PMOD PCB breakout board. And so there's a couple layers of this. One is, okay, we need to turn on this OLED controller, and then 2, we need to communicate with it. And so, it's basic SPI protocol where when you pull the chip select low, you're enabling that OLED controller. The master out slave in is going to be a serial communication protocol similar to UART, but instead of agreeing on a baud rate, the master SPI module will drive the clock for this SCK serial clock. And so the frequency of this clock is divided down based on the requirements from the OLED display driver. And so it requires a frequency of maximum of 5 megahertz. So then I divided that down with a plus 20 counter from my 100 megahertz Bassett's 3 clock. And then if that was still too fast or things weren't holding up properly, then I could instead slow it down and divide it down again. And again, with the data command control, this is another bit that is read alongside the serial bit here. So you can see there's the schematic. So when you want to write a command, you will tie the DC pin low. If you want to write data, which would be the color bits for the pixel, you would tie it high. A command would be setting the row or column address followed by the starting ending row or column. But you can see kind of here how you pull the chip select low. The data command can vary, and then based on your MOSI or SDN here, the OLED display driver would read those 8 bits, and then pretty much on the positive edge of the S clock, it will read the bit. So you kind of get this weird offset of where you need to be updating things on the negative edge of the clock so that the receiving end can take them in on the positive edge. Otherwise, you're going to have a timing error and you're going to have to slow everything down a lot. And just to make sure everything's stable. And this is kind of similar to sampling 16 times and taking the middle bit of UART. So, let's see. We have some timing stuff here. Like I said, the minimum S clock cycle time is 150 nanoseconds. For the total cycle time, then it has more specifics here, but we just generalize it to that. So it's got a maximum of, I guess, 6.66 megahertz. So we stepped it down to 5 to have a little bit of wiggle room. Then there was the reset and power on sequence, and this was explained through Digilent, the PMOD I got. It's pretty straightforward. It's probably faster to just step through that in the state machine. And let's see here. I guess we can just step into the code and then we can jump back into this stuff. So I did this a couple ways. The first thing I imported was a clock divider because, like I said, we know that, oh, well, we can't use our 100 megahertz clock to drive this thing. So we just got a clock divider that we used from before and divided it down based on what we needed, based on knowing that's a 100 megahertz clock by default. So this module, in-bit MOSI SPI, is used to send each individual bit, and also, so it's going to drive the master route slave in bit. It's going to read the data for each pixel and the commands. The chip select bit, which determines when the OLED controller is enabled and when it'll start reading data. The data command bit, ODC, and then it also will send a flag bit when the second to last bit is being transmitted. And that's important because it's not the last bit, so that it flags when the next byte needs to be loaded so it can concurrently keep sending bits without being sent back to an idle state in between and have dead time. So, like most state machines, when the asynchronous reset is pressed, then the state gets reset back to idle, and then all the data gets zeroed out. The chip select does get reset back to 1 because it is active low. And whenever the chip select goes to 0, then the OLED controller is going to start expecting data. So I don't want to accidentally get flipped there. So this is pretty straightforward. The biggest thing too that's interesting is notice here how the input is IS clock. So it's going to be divided down from the clock divider. So these bits are getting updated on the negative edge of the shared clock between the master to the slave. Because then on the positive edge, half a period away, it's going to be reading these bits. So you don't want to update them both on the positive edge and have it read on another positive edge. You might be able to get away with it, but you also might come into some really bad timing constraints. So it's better to give that half period buffer in between, especially since it's pretty easy to just say neg edge here and then work your way up on the rest of the design from it. So when it's in the idle state, it's pretty much waiting to receive this start bit. So this is going to be driven higher up later on, basically by the OLED interface to determine when are we transmitting data. Do we need to just keep going all the way through? Do we need to wait to load something else in? That's abstracted here up to be controlled by something else. But when it is started, it goes to the transmit state, which is updated by our state register here. And then And to note, these are synchronous, and then they have a asynchronous reset. I tried something a little different where I didn't denote every single reg type in every single state just to cut down on the amount of code needed. But it'd be pretty fast to fall into a latch state, so these were tested pretty heavily. And so pretty much what happens here is whenever you begin transmitting, if I start is asserted to 1, then you pull the chip select low, so you'll start receiving data on the next positive edge on the slave of the OLED receiver. You'll pull in the input to output it for if it's a data or command byte. Again, this isn't something we want to determine sending bit by bit because it'll be handled by the LED display controller module, which will determine are we sending something to initialize or set up the display, or are we sending information on the color of the pixels. So then it has a registered account, what bit is being transmitted, and then it also, as it's entering this state, it does load up the first bit again just to save on the number of cycles that this is going to require to transmit every pixel through the screen. So if it's so it starts with 1 because it loads them in at the same time. So then on the next state it'll read 1. If it's a 0, then it will update the DC value since that was instead done in this initial state. If it's the second to last bit, it will raise this final TX bit. We're saying on the next positive edge where it's loading byte to byte, we need to prepare to load something else up. And if it's the last bit of the byte, so you have with -2, and then I did greater than or equal just to catch it, just in case there's a glitch. Then it will basically determine if it wants to stay in this mode and just keep transmitting for another byte, and if not, it will go back to the idle state. And this was pretty interesting to test, with a test bench. With this, it wasn't enough to directly communicate with the bit unless I wanted to control each data command bit with these inputs separately. So I followed to create the in-bit MOSI SPI buffer module. And so this takes some very similar inputs, which is the S clock driven by the master, the asynchronous reset, and then it takes I data, which is going to be it can be multiple bytes to transmit, or it can just be 1. It's an array of however many bytes and the width of how many bits you're transmitting times the number of those sets of bits that you're transmitting. And so this is nice because you can choose, I want to transmit 4 bytes in a row because that's the command protocol that it's going to require. I only want to send 1 byte this time, or 2 bytes. And so one place where that's useful, for example, is, let's see. So for setting the column and row address, so you can notice here that the data command bit is always pulled down to 0 for each of these. I made a mistake where I thought that the actual row addresses and column addresses had a 1, and so I was getting some glitches from that. But you can see here it has a certain opcode to send the command of setting the column address, and then right after it, you send the start address and the end address. And so it makes a lot more sense when you're transmitting these from the top level OLED controller to just load all 3 up at once, push them away, and then wait until they're done instead of having a separate state for each of them. And it really cut down on the number of states that I needed for top level. So it worked out pretty well. But as you can see here, we have this on the positive edge. So what happens is on the negative edge, each bit is getting transmitted out. On the positive edge, it's determining if we need to load in a byte or another set of bits to push out. And so the logic is very, very similar for this module. It's just working at a byte level instead of a bit level. And it's also on the positive edge. Looking back, I think I could have combined these 2 modules, but the way that I was working through it, step by step, I'm kind of glad I kept them separate, especially if I wanted to work on them more or change them more radically. But then I created this buffer combined module just so it was easier top level with the OLED interface if I was able to instantiate both of them together and just keep some of these wires between them because I was instantiating a bunch of wires for another module and it just seemed excessive. So then you can have the bit to bit transmit and then the byte to byte transmit in the same module, and then you have some very similar IO to them. So at this point, it was a question of okay, we can send individual bits on the negative edge. We can drive the chip select, we can drive the data command. Um, how do we actually turn on this PMOD board and get something displayed? And so that's where the OLED interface module comes in. This is a little longer. It gets pretty complex, or more complex. It's not too bad. But the way that this works is it handles the turn on sequence initially. And so we're going to ignore a lot of this for now. But some of these inputs are, so it's going to take a 8-bit input for the text color and the background color. It's going to take a input for each of the 1 byte ASCII values in an array. It's going to output, let's see here. I don't even think I used this. Well, I did. Oh, never mind, I did. So I guess I had a ready bit so that it showed you when it was ready to start writing, but I just had it kind of off the rip write forever for the ASCII display. That's something to look into. But so it takes in the default clock, and then that clock is divided down in this module. Async reset, same thing. iMode is to determine what type of display you want. I just had a very standard fill all the screen with a blank color to get started, like you saw, which was kind of similar to this, but without the text on here. Maybe something more like this, but this wasn't a black screen. But yeah, and then we also have the same output. So you have to think about this modular where we have the output for the bit level, byte level, OLED interface. That goes all the way out to the output wires of the FPGA to the actual board. So the chip select bits, or the chip select output, the MOSI, the S clock, the DC, these all have to come out of this controller because these are what's going to be driving the actual chip on the breakout board. Alongside this, there's some other outputs. ORES is a reset pin for the OLED interface. OBCCN and OPMODN are used to enable parts of power to the board, so those are driven active whenever it is turned on. And then we also have OMOSI final bit and OMOSI final byte, so it indicates the final bit in each byte transmitted, and then the final byte that's being transmitted during a set of bytes on a load to the byte buffer. And so a lot of these parameters are just constants used. It's nice to have these here so you can change them on the fly, both for if your synthesized module changes or for a test bench so you actually can run it in the amount of time, because I don't want to sit here watching hundreds of thousands of bits transmit at a time. I'm not going to get useful information from that. It's not going to complete. And so we're going to scroll down here. So we instantiate this buffer combined module that we talked about before and the clock divider that we talked about before. This ASCII output we'll get to in a minute. And so, like I said, this also is happening on the positive edge, async reset. So the only thing happening on the negative edge is the bit-to-bit output for the SPI write. And so with this state machine, if on a reset, this register sinitReg is set to 0. So if on reset, this is written to 0, it will immediately begin to initialize. And this is really nice because when you hit the reset, you don't have to send any controls directly. It will just power up on its own. So then the question is, well, what happens in this turn on state? Well, based on iMode, I guess if it's the case where it is initialized and you can choose what mode it's in, this can either be hardwired to the module and you instantiate it so that you don't need to choose, because if you hook it up in a module like I showed for this example, where you know that you want to display ASCII, you don't need to flip-flop between this and a solid screen. But maybe you want to. Maybe you want to have that as a switch on the dev board to choose, or have different modes of different types of ASCII display. It's very easy to change once the template's here, and that was the goal. So in the turn on mode, there's a few things that happen. I will go back to. So what you do is you power on, you give the board VDD and VDD-IO. This is just done by powering the board through the VCC 3.3 volt lines hooked in through the PMOD. After that's stable, the stability, it asks you to wait 3 microseconds and then it'll move on to the next state. So you want to set the reset pin low. You want to wait for power to occur. And then you want to, after 3 microseconds, set the res pin to high. You want to also wait 3 microseconds to power on VCC. So you'll see here, res set to 0. You wait 3 microseconds, and then VCC is turned on, PMOD N is turned on, and their power enable for more efficiency. Saturates a MOSFET. And then ORes is also driven high. Then you wait another 3 microseconds, and this is just done with a basic counter that I've done many times. You go to the next turn on state. And then here, you have to send stuff through the byte buffer, and this is the payoff here. And so instead of doing 3 separate states to send each of these bytes, you can load them all up in a chunk, send them on their way. And so they will be read from the least significant byte to the most significant byte. So this first code here will be sent first, AF. You can see here we can set the data command bits for the lowest 3 bits that'll be read, and so you can see that they're all command bits. You might be wondering, oh, well, what's that AF command? So that's what this table is for, which is a reference manual. And display on. Yeah, I guess that is it. How about there was another mode after reset? My bad. So yeah, 0xAF is pretty much to set the display on in normal mode. There's a bunch of default values that occur after it's reset, but it sets the default row and column start and end addresses. And so you turn the display on, and then you use this other command called A0 to do a master configuration update. And so A0 is a very handy tool. If I can find it. I guess it would be higher up because it's in hex. Yeah, so remap and color depth setting. So every bit has mostly a setting. The big one we care about, one of them, is this color format mode. So on default, which is what this right column is, you can see here that's in 01 or the 65K color format. This means we would have to send 16 bits for every color, and it would have 65,000 different color options. Or we can choose to send 8 bits and only have 256 colors. I'm not planning to display images at the time, and I wanted to want the display to update faster, and so it would update twice as fast, and so it would have to send twice as many bits for each pixel. So I updated that since we were already testing everything, sending it 8 bits at a time, and it's kind of similar to. So we updated that. We also had to update another bit, which was. So this was the command, and then the following byte was the control bits that it sent. So you can see here we sent A0, and then the following 8 bits are the controls. So we wanted to make sure everything else stayed the default values except for A5. So A5 enables the odd-even split, which this is very much needed because I found an issue where before I had this, let's see, where is it? Before this, it was writing the addresses to row 0, row 3, row 5, row 7, and then once it went through all the way halfway, it would come back up to the top. And so my display was getting cut in half. And so with this bit, we're able to make it so it would go concurrently down. And this was really interesting because this was also an issue I found when I was TAing in my embedded systems class. And so it was a really good learning opportunity to learn about writing to specific addresses. But that's done there. And then they're all command bits. And then you choose SN transmit. You say, I'm sending 3 bytes. And so then it needs to send all 3. Then you send the start signal to it. Then you go to the next turn on state. And then you pretty much say, I don't want to transmit anything else. And then you have a counter that waits 100 milliseconds to go back to the idle state. And so pretty much just part of the turn on sequence is saying, after you set the display on command, you need to wait 100 milliseconds, and then you're good to go. Then you can start transmitting whatever you want. And so then I was like, okay, well, starting with ASCII stuff might be a little tough, right? So I wanted to start with the fill screen state. And so this is where that mode selection comes in, where I can just use 2 switches on my FPGA to pick the mode, and then I can hit I start, which is just a debounce button, and I can say, take me here. And so then you can see it saves in this 8-bit register, reg type, the input background color. So then it'll just fill the entire screen with one colored pixel. And so my question was, if I pick the right 8 bits, will it show the right color? It did not right away. So you know how I was talking big game about the color configuration. So I added in these 3 bytes, and then I just scanned the same bits. I think I put in 0, 1 like the default instead of 0, 0. So I was expecting 16 bits every transmit. And so I was getting messed up colors. It was only displaying about half the values, but that would make sense because it was receiving, for 1 pixel, it was receiving what I was expecting was 2 pixels. So when I was trying to get more accurate outputs with the ASCII display, it did not work. But luckily I had this reference manual, and I was doing pretty diligent notes at the time, just following all this. So I eventually found it. But this fill screen state is just one mode, and it just writes as data. It just transmits 1 byte. It signifies it's a data command, or it's a data bit byte, not a command. And then it just transmits 1 bit, and it just starts the byte buffer. And then you can just hold the button down and go and go and go and go and go. And this is how you would just get a solid color, minus this. And then you could pick between the switches to say, I want this color, I want this color, I want it to be green, and then blue, and then red, and then blue, and then green, and then blue. And that was fun. That was very rewarding. I guess I got a little ahead of myself. Before I got to this is what the screen looks like after the turn on state, after nothing is written to it. So I was able to do that first state, and I got to this. And even though this looks like crap, it was still really exciting. But then I was able to just display a blank screen, if you imagine all 1 color. That's pretty exciting. But then I was like, oh, let's see if we can see something. And so then we go to the next state. I think this is really cool because it's only 2 states. So this is what I call the pixel display state. So this saves a text color and a background color reg, and then it resets a couple things. So with the ASCII values, there's a lot of parameters implemented to generalize it. And so numCall is the number of pixel columns. NumRow is the number of pixel rows. So it's 96 by 64. And then the ASCII call, ASCII row size is number of pixels that would be horizontal and vertical. So it's an 8 by 8 ASCII. And then that 8 by 8 bits or pixels of ASCII can be represented by a 1 byte ASCII code. So for 64 pixels, you just have to save 1 byte. And then if you already save a preset background and text color, then you can just save 1 byte for the entire set of colors. So then you don't have to save 96 times 64 times 8 bits, because it's just gonna take up space on your FPGA that you do not want. So everything's getting very abstracted here, so it's very easy to update because I've also seen on Digilent they have 128 by 32 pixel displays. So if I wanted to make this more generic for the future, I could. Or maybe there's one baked into an FPGA dev board I get eventually. I would hope I could use most of this again, and that was kind of my goal in designing it like this. Is I want to make code that's reproducible and that I can actually use in the future, and it's not just going to be forgotten about. So that's kind of my thought. But then we just have a bunch of internal wires that keep track of things. S ASCII first column and last column, first row, last row. These are wires that are pretty much assigned just so they can be referenced and transmitted easier. So we'll get into those. So in the first state of pixel display, we have to set the starting row and column addresses and the ending ones. So you'll see here that we have 6 bytes to send, 3 for the setting the column addresses, 3 for the rows. The first byte you send is the command byte saying, hey, this is the opcode for what I'm doing. The following 2 are saying this is the first column address, this is the last column address, like we saw in the documentation a little bit ago. One of the first ones. Yeah, so pretty much it just runs through these 6 bytes. And you'll see by the default it goes 0 to 95, 0 to 63, which are the dimensions of our OLED display. But we want to show an 8x8-bit pixel, exactly like this. And if this wasn't here, it would go 64 all the way across in a line, but that's not how you're going to see a full ASCII value. Otherwise, your A is going to look very stretched out, and then all your letters are going to get peeled apart. So that is why this is here. SDC is updated. We are transmitting 6 bytes. We are going to start transmitting it, and we're going to go to the next register. And so S pixel count reg is each pixel that is sent. Now remember, each pixel is a byte of color bits. So we have to count all the way up to 63. So you can think of it as, we'll go to MS Paint. So we've got, let's see, 90, oh, that's so small. 96, 64. And then we've got a 8x8. So this is one ASCII value. And then, there's 8 rows of these, 12 across. And so inside of this, we'll just try and draw this. We could transmit A. And so what I did before having an actual bitmap converted, I just hard-coded the 64 bits for this A value that was input into this OLED interface module. And so one other thing you'll notice is S ASCII takes in the input of I ASCII, which, let's see. So I ASCII is the entire wire that's going to be used from a register type to go into here. And so before is just abstracted as this A value, which is why we got this. And so everything was depicting an A because we hard coded it to just depict that one A before we expanded it to read the entire ASCII array. And so here it's saving it under ASCII, which set to 0. Okay. So then what we do is we will go down here. And so after we determine the start and end row address, and so what we would do is we would go line to line, to line to line, 8x8x8 until we're done. And then I can do this square. We would go to the next one. And so before we get to there, I'm getting ahead of myself, I'm sorry. So after the first state, we've determined that these are the start and end addresses. Pixel display 2 is going to show dot 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 line 8 by 8 pixels. And so pretty much, while we could load it like a row of bytes at a time, I think that would cut down on some of the internal registers needed for the reg type. I just did it 1 byte at a time to keep it a little easier to manage. And so pretty much what it does is because you remember, you have to send 1 byte at a time, but you have to wait until you're on the second to last bit and also the final byte. But every transmit's going to be the final byte. So it's a little redundant, but we could update it in the future. So here, if the pixel count is above the size of the ASCII pixel dimensions, aka it's transmitted all 64 bits, you will determine how to leave. And so basically, this is just like your edge detection. So, if you're on the last edge, you're going to reset your column back to 0 and increment your row. If you're somewhere in the middle, you're going to stay on the same row and increment the column. If you're on the very last one, you are going to be done. And so this is pretty standard stuff, just with like for loops. It's just implemented with counters and concurrently with FPGAs and state machine. And it's pretty straightforward once you get through it with the logic. But you can kind of use it like pseudocode, treat it like high-level synthesis, and then convert it into a state machine. But yeah, so this is how we got to here. And then the question is, how did we get here? So now we're trying to display separate text ASCII values. And so, like I said, we then take an input and then we increment through it for this long stream of ASCII byte values. And then what we did is, if we look at this from the synthesized top level module, we have a button latch. I had this wire, and we also instantiated the OLED interface module that we were just looking at for a pretty long time. And so what I did was, for this, I assigned this SASCII wire. And it's really interesting because Verilog will actually take in quotations ASCII text. And so I can just write in a 12 by 8 kind of grid. And so the way it's broken down is it just reads as one full array of bytes of ASCII values, 12 times 8 of them. Jake is good at writing Verilog for FPGAs. And so obviously these ASCII values on their own aren't going to be read. And so instead you have to use a module that's made in here called the ASCII font 8 by 8. And so this would have also been required to display any text. And so this is disgusting. This is where the fun part comes in. So it is just a beautiful case statement where it takes an input that is an ASCII byte. It decodes that byte into basically just an ASCII table of 8 by 8 bit pixels. And this is when I discovered that, it was flipped backwards. So then we have these assign statements. So then O pixel 7 to 0 is flipped. So then it goes 0, 1, 2, 3, 4, 5, 6, 7 instead of 7, 6, 5, 4, 3, 1 the other way. And so then this was pretty easy to verify. And so that was the intent with this, where I just hard coded the input to this module as iASCII, and then I had it flood it with OPixel the whole time. And that was kind of my thought there. So now we're at this point, and I was like, oh crap, I gotta flip them over. So then we got to here, which is what we saw at the top of the synthesis, which was done right here. So you can see I can hardwire any type of ASCII characters I want in Verilog. Say Jake is good at writing Verilog for FPGAs. And this was just really cool. I was really excited with this, and I thought about a lot of opportunities I can apply this to, like I said. And I wanted to apply it to something before I finished this. And so that was again where I had the timer. And so you can see here, based on the state of the reaction timer that I talked about earlier, and I showed off previously last December, about 8 months ago, that I can apply a state machine that I derived before, add an ASCII text state machine to basically to tell, based on the state machine here, we're going to use a case statement to pretty much output different copies of the text color, the background color, and the actual ASCII values. And so this was not that hard to implement after having everything else done. And so I just imported this reaction timer code. It worked already as a BCD counter, so I didn't even have to do like a binary to ASCII conversion like that, because it was displayed on the 7-segment display in BCD before. And so pretty much what I did is I just created these case statements where I had a conversion from hex to ASCII. So pretty much the hex display that I would normally read on 7-segment display was converted to the 1-byte ASCII codes from the 4-bit hex values. So it just goes 0, 1, 2, 3, 4, 5 to 9, and then A, B, C, D, E, F for hex and the ASCII values. We also had a debounce module, but the main thing to decode it was in this reaction timer ASCII module. And so with this, we have the 4 inputs, hex 3, hex 2, hex 1, hex 0, which were the 4 hex values that were before only shown on a 7-segment display. And we also included an input for the state of the reaction timer, and then a fail state, which determined if you failed too early, failed too slow, or you didn't fail at all and you actually won the game. And so you'll see with the output, this is the same sized O ASCII, which is the entire string of 12 times 8 bytes of each incremented ASCII value. And the most significant byte is the top left ASCII value, and the significant byte is the bottom right ASCII value, like this. But yeah, so then we instantiated 4 modules of those hex to ASCII modules, and so then it just converts them all alone. And then we have a state machine, so then based on the state of the timer, so if it's 0, 0, then the indicator, it's just waiting to begin the game, so it says press to begin, good luck. You can choose a black background and a white text screen, and then these text colors will be saved before it starts transmitting, so it'll have the same color throughout and not have a glitch. And then when it goes to the next state, it is going to wait to hit the blue button so you can't get antsy. So it says press the button when blue, and then the background is still black. And then it's the react stage where the background turns blue and you have to hit the button within a second. If you do, you'll get a reward with a green screen, and if you fail and you don't hit it fast enough, then the screen will go red and it'll say you're too slow. If you hit it too soon in the random count stage, then you will get another fail screen, like I said, because you're too early, too ahead of it. So then you can see those 3 states here in the done state after the game is up. Because then based on this fail state, you can see 3 different options. And so it's the coolest thing about this is you can wrap in these converted hex and binary values into 1-byte ASCII codes and bake them in. And so based on the time, you can see the counter up to 1 second. Reward you or it can fail you. And this is really interesting because I'm probably just going to keep copying this format of this module for whatever I do in the future, because I see no reason to try and take more time to be crafty and get a display that's readable on a 7-segment display when I can just type in stuff in a string in Verilog and then see it on my board. And this is the biggest sell to me, is it took a lot of work to get the SPI module built and the OLED interface based on the datasheet. This part with the interface, once I got the text displayed with one wired thing saying I'm good at writing Verilog, it wasn't that bad because, this is just a case statement. This is just wiring up some bit conversions. That was it. So yeah, that's kind of where I'm at. I guess I'll play this one more time. But this project was really rewarding. I can't wait to see how this gives back to me in the future. I can't wait to apply it to more things. Um, it's been a really, really challenging project, especially over the summer for me. But yeah, it's been good. Thank you so much for watching. I hope this was entertaining. This went longer than I thought, but I think this is a good video. So thank you so much for watching. I hope you learned something. Hope you learned a little bit more about me, maybe you. Thank you.